In this module, we shift our gaze to Act 2 of the lecture. We'll look at the revolution of scientific revolutions. Specifically, we'll go through timelines covering 50 years, starting at 1877 and ending in 1927. Our first timeline will chronicle discoveries in the natural sciences. The second timeline will focus on mathematics and logic. The third timeline will integrate features from the first two timelines together with discoveries from psychology that we discussed in the psychology chapter. The productive confluence of categorization, operationalization, and experiment at the beginning of the 20th century is not unique to scientific psychology. The end of the 19th century and the beginning of the 20th century witnesses a rise of a newly robust science in many fields. Indeed, the developments in these fields act to synergistically accelerate the pace of developments across all fields. Physics and chemistry in particular witness a number of dramatic advances that tear apart the older orthodoxy. Within a period of approximately 50 years, from 1877 to 1927, the groundwork for atomic physics, atomic chemistry, quantum mechanics, statistical mechanics, and space-time physics falls into place. For instance, the Austrian physicist Ludwig Boltzmann makes the first tentative moves towards statistical thermodynamics when building on Maxwell's 1871 work. Boltzmann publishes two famous papers. 1872 sees Boltzmann publish further studies on the thermal equilibrium of gas molecules, in which he introduces his Boltzmann equation and his H theorem. Boltzmann claimed that the latter proved the second law of thermodynamics, while the former describes the statistical behavior of a thermodynamic system when not in a state of equilibrium. Boltzmann addresses potential difficulties with the 1872 paper in his 1877 paper concerning the relation of the second law of proposition of the mechanical theory of heat and the theory of probability, respectively the theorems about the thermal equilibrium. William Ramsay and Lord Rayleigh published argon, a new constituent of the atmosphere, in 1895, marking the beginning of the discovery of noble gases and ultimately an expansion of the periodic table. 1897 sees J.J. Thomson publish cathode rays, in which he discovers the electron. In 1901, Max Planck publishes On the Law of Distribution of Energy in the Normal Spectrum, in which he introduces Planck's law to calculate the electromagnetic radiation emitted by a black body in thermal equilibrium at a given temperature. Planck's paper introduces the idea of quantum theory to physics. Albert Einstein's miracle year in 1905 sees him publish four famous and foundational papers. On a heuristic viewpoint concerning the production and transformation of light, adapts Planck's work on blackbody radiation to explain the photoelectric effect. Investigations on the theory of Brownian movement describes the motion of pollen molecules in a liquid using statistical mechanics. Importantly, Einstein demonstrates the existence of atoms, the reality of which were debated, by showing how one can count them using an ordinary microscope. These two papers taken together lay the groundwork for the coming atomic physics and for quantum mechanics. On the electrodynamics of moving bodies introduces what we now know as the theory of special relativity. More specifically, Einstein reconciles Maxwell's work in electromagnetism with the classical mechanics by introducing the principle of relativity and the principle of the invariance of the speed of light. Finally, in Does Inertia of a Body Depend Upon Its Energy Content, Einstein deduces his famous equation, E equals mc squared. Einstein's former mathematics professor Hermann Minkowski publishes Space and Time in 1908, in which Minkowski provides a space-time geometry to subserve special relativity. Ernest Rutherford publishes The Scattering of Alpha and Beta Particles by Matter and the Structure of the Atom in 1911. In 1913, Niels Bohr publishes On the Constitution of Atoms and Molecules, parts 1, 2, and 3, in which he modifies Rutherford's account within the framework of quantum mechanics. The resulting theory of atomic structure goes under several names: the solar system model, the Bohr-Rutherford model, and the Bohr model. In 1916, Einstein publishes The Foundation of the General Theory of Relativity, outlining the theory of general relativity and completing the reconceptualization of gravitational physics. In 1919, Arthur Eddington travels to the African island of Principe and provides photographic evidence to support the general theory of relativity. Specifically, Eddington photographs light bending around the sun during the May 29, 1919 solar eclipse. 1925 sees Wolfgang Pauli publish on the connection between the completion of electron groups in an atom and the complex structure of spectra, in which he formulates the electron version of the Pauli exclusion principle. Pauli's principle allows one to derive the properties of electron shells, both the orbits and the number of possible electrons in each orbit, by demonstrating that no two electrons orbiting a single nucleus can have the same quantum state. Edwin Schrödinger publishes an undulatory theory of the mechanics of atoms and molecules in 1926, in which his Schrödinger's equation provides the mathematical framework for the wave model of atomic structure. Werner Heisenberg publishes the quantum theoretical reinterpretation of kinematic and mechanical relations in 1927, wherein he states the Heisenberg uncertainty principle. Heisenberg's uncertainty principle states that the precision with which one can determine the position of some particle varies inversely with the precision with which one can determine its momentum. Thus, the period beginning in 1871 with Maxwell's book on heat and ending in 1927 with Heisenberg's paper on uncertainty sees a fundamental reformulation of thermodynamics, chemistry, and space-time physics, as well as the birth of atomic physics and quantum mechanics. Theoretical models move from exceptionalist universal deterministic laws towards statistical, probabilistic, and relativistic models. Finally, the American Percy Williams Bridgman forwards the doctrine of operationalism in his 1927 book, The Logic of Modern Physics. The book and its author intend the doctrine for physics primarily, though it inspires a number of psychologists, including the neo-behaviorist Edward Chase Tolman. Bridgman, inspired by the theory of general relativity, as well as his own prowess as an experimental physicist, identifies theoretical concepts with the single, unique procedure for their measurement. The doctrine remains somewhat ambiguous regarding its status as a theory of meaning, though it naturally lends itself to such an interpretation. It also suggests that progress in the sciences is fueled by categorization, operationalization, and well-designed experimentation as much as creativity or the intellectual or intuitive insight of an isolated genius.